Hey guys, in this video I'm going to show you another example of finding the gradient of a function and evaluating it at a point and then finding a directional derivative using the gradient. So common exercise in multivariable calculus, and this will involve a function of 3 variables, so you've got to be patient because it is quite elaborate, so you've just got to keep a smile on your face. Alright, let's take a look. This is my friend over here, is going to help us from time to time. Let's begin. So the function we are dealing with in this exercise is the following. And I have to switch to the finder point here because it'll fill up the page fast. So you've got here f, okay? Well, it's not clearly visible, let's try a darker one. So you've got f of x, y, and z. Okay, so the function is f of the variables x, y, and z. And this is defined in our exercise to be the following. Cosine of the product of x and y, and then you have plus e to the yz, and then as the last part you have plus, I'm going to move you, buddy, ln of zx. Okay, so when you first look at this, you've got to say, man, that looks a little, it's like scary. Okay, but this procedure is still fairly mechanical. So the first step is form the gradient, evaluate the gradient, take the dot product of the gradient with the unit vector, and that then will be your directional derivative at a point. So the point in our case is the following. P equals 1, 0, 1 half. So that is our point. And the vector that gives the direction for finding the directional derivative is a equals I plus 2j, and lastly plus 2k. So these are the key pieces of information. The function f of x, y, and z. Then you've got your point 1, 0, 1 half. Then you've got your direction vector I plus 2j plus 2k. Once you have these pieces, now you apply the following procedure. Form the gradient of the function. So this means you've got to remember now how to take partial derivatives because the gradient consists of the partials put into a vector. So with respect to x, you can use the chain rule on the cosine here, and what you have is the following. Cosine of xy, so you differentiate the outer function as negative sine of xy, and then the derivative of the inner xy with respect to x is just y. So you can place a y on the outside like this. Okay, so minus y times sine of xy. E to the yz doesn't vary with respect to x, so it goes away, it's constant. And then ln of z times x is the following. You differentiate with respect to x, so you have plus 1 over zx, and then you use the chain rule, so that gives you another z. So notice the z's will cancel eventually, right? So this is just the raw step here. Okay, that's the first step. Then you add to this. And I'm going to bring this down to the next line so I don't hit the A here. Add to this the derivative with respect to y. So what you will have is same principle. You've got to use the chain rule here and then use it here. So you have negative sine of xy, and then when you differentiate the inner portion, all that remains is x. So place the x here. Then differentiate that with respect to y, which will be by the chain rule e to the yz, and then when the y differentiates away, all that remains is z. So you've got that. Now, this term does not vary with respect to y, so its derivative is 0. So enclose this within the parentheses, and this is the j component of the gradient. Now to this, you will add the z component. So cosine of xy is constant with respect to z, so it differentiates away. E to the yz you differentiate by using the chain rule, so you have e to the yz, and then differentiate the z away, all that remains is y. Likewise over here, you differentiate that using the chain rule, so it's plus 1 over zx, then you differentiate the z times the x with respect to z, so all that remains is x. Now this becomes the k component of the gradient. With this in place, the next move is this. Simplify a little. Negative y sine of xy plus cancel the z's. You have 1 over x I. Then you've got, and here you have to be so careful because this is multivariable calculus. These procedures are elaborate. One mistake can cost you 20 minutes, wasted time. Speaking from experience. So what we have now is this. Plus negative x sine of xy plus ze to the yz. Man, this is elaborate. Okay. Simplify the k components. You've got ye to the yz, ye to the yz, and then you've got cancel off the x's, and all that remains is plus 1 over z, and that's the k component of the gradient. Right, so this is just the gradient that we have found by using partial derivatives and plugging them into a vector. And the gradient is just a glorified slope. That is all that it is, nothing else. Okay, so with this in place, the next move is you got to evaluate the gradient at the point 1, 0, 1/2. Okay, so you've got to evaluate the gradient at that point. You see he's still smiling, so you've just got to keep going. Persistence, persistence, persistence. Let's do it. So the gradient evaluated at the point 1, 0, 1/2. Okay, that will take a couple of minutes. Negative y, so that's 0 times sine of 0, that's all 0. So that goes away. Then you have 1 over x, but that's just 1 over 1. So all that remains, thankfully, is just a single I. Okay? Then you have to add to it negative x, which is negative 1 times the sine of 1 times 0, which is 0. So that gives you 0 again. And then you have z times e to the yz. So now that is 1/2 times e to the 0 times 1/2. That's just 1/2 times e to the 0, which is the same as just 1/2. That's it. And lastly, we have y times e to the yz. I'm trusting you to be able to fill in some of the written details by hand, right? You've got to be able to do that on a test. So you've got your I plus 1/2 j, and then you've got your y times e to the yz plus 1 over z. So where you see y, replace it with 0. Where you see z, replace it with 1/2. So firstly, if you place the y in front of the e, that makes that whole term equal to 0. So it goes away. Then all you have is 1 over z. So that's the same as 1 over a half, which is 2. So you end up with 2k. So this is the vector, the gradient evaluated at this point, 1, 0, 1 over 2. Okay, so with this in place, the next move is you've got to find the gradient vector, well, that we've done. Then you've got to find the unit vector in the direction of a. So u equals a divided by its magnitude. So you've got I plus 2j plus 2k divided by the magnitude, by the length of that vector. How do we find it? Well, these are the symbols. You applied the Pythagorean theorem on the components of a. So you've got here 1 squared plus 2 squared plus 2 squared. So that gives 1 plus 4 plus 4, which gives the root of 9, which is just positive 3. So the length of this vector is 3. So you go over here and you divide each component by 3. So you've got now 1/3 of I plus 2/3 of j plus 2/3 of k. Now that we have this, comes the crucial step of taking the dot product of the gradient and the unit vector. So we will take the gradient evaluated at the point 1, 0, 1 over 2, and we will take the dot product of this with the unit vector. So let's do that. So we've got I plus 1/2 of j plus 2k. We will dot this with 1/3 of I plus 2/3 of j plus 2/3 of k. So I dotted with I, of course, is just 1/3. Okay, so 1I dotted with 1/3 I is 1/3. Add 2 with 1/2 j dotted with 2/3 j. That just gives you 1/2 times 2/3. And the last one is 2k and 2/3 k, so that gives you 2 times 2/3. Okay, so this is the basic dot product that we are applying here. So with this, let's simplify this. And now the rest I will write in a dark marker. It should fit on a page. Let me even trace this over. So 1/3 plus 1/2 times 2 over 3 plus 2 times 2 over 3. So you've got 1/3 plus another third, right? 1/2 of 2/3 is another third. And then we have plus 4/3. Okay, so we are just about there. This guy's still smiling. So we've got a 1 and a 1 and a 4. Okay, so that gives altogether 6 over 3, which is miraculously just a nice little number, positive 2. So despite the elaborate procedure, this procedure is still fairly mechanical. This is the function. Take the derivatives, plug them into a vector. You're given a point and a direction vector. Evaluate the gradient at the point. Take the vector, turn it into a unit vector by dividing by its length, as I've done here. Take the dot product of the gradient and the unit vector, as I've done here. And the output from this is the value of the directional derivative at the point. Okay, this guy is smiling. He's like, yes, we are finally done. Yay. Okay, and remember, this is a positive value, which means that in the direction of this vector, this function is increasing. And that is it. So thank you for watching, and stay persistent.